Welcome to the first lecture of power system protection. In this lecture, we will see the need of power system protection and a very brief introduction to the different components of power system protection. Now, why we protect power systems? Why we protect power systems? It's against equipment damage, then interruptions, it's against interruptions, and what else? So basically this improves reliability. And security. Right. Now we'll see an example. If a small portion of insulation is failed in a transformer, the conductors may touch each other and high levels of fault currents may flow. If the fault current is not interrupted quickly, then there is increase in temperature. That will cause a rise in temperature, which may fail the surrounding insulators also, which leads to spreading of the damage or spreading of the fault. So the fault current increases and later it may lead to melting of conductors and damage of the steel laminations itself. So finally it can cause a catastrophic damage. In worst case, it can cause a catastrophic damage. So this is the final consequence. This can be the worst consequence. So to avoid this, we need to design and operate the protection system properly. Now, what are the possible faults in the system, in the power system? Natural causes of faults could be lightning. It could be lightning. Then wind. Then ice and snow. Because of these causes, see the second and third aspects, they mostly result in touching of two conductors, which may give an extra path, an additional path for current to flow, and this will lead to short circuits. Okay, short circuits. Now, lightning is, of course, this is intermittent. But it may cause a permanent failure also. That we don't know. That depends on the type of lightning, the voltage involved and other things. We'll see it later. So a broad categorization of faults can be intermittent and permanent. What are intermittent faults? Common causes can be lightning, as we already discussed. It can be lightning strike on the transmission line. Then a strong wind causing two faces of the transmission line to touch. So wind, two faces of the transmission line to touch and form an arc. If they touch, then it forms an arc. And if the arcing is prolonged, if the arcing happens for a prolonged period, then the surrounding air it's already ionized. That is why there is arcing. But the air itself acts as a conductor. Then what happens? Arc is maintained by the power in the line. If there is a high power carried by the line, then the arc is maintained. Then the protection system responds by removing this power from the line for a period of time. and the duration of this isolation or this the removal of power from the line, the duration of removal of power from the line should be long enough to allow the ionized air to dissipate, and the line is recharged, or the line is the power is reapplied to the line. So this is basically intermittent fault and how it is dealt with. Now, what about permanent faults? Permanent faults are physical damages, mostly physical damages, falling of trees, then falling of the line itself, then what else? Protection system should quickly sense and isolate the faulty components to minimize the damage. Here also it is dealt with in the same way, but it should quickly be sensed and it should be isolated. The faulty components should be isolated to minimize the damage. So one requirement is to minimize the damage. Okay. Now, to keep the power system operational without any interruptions, how should the protection system be designed and how it should be operated? The specifications of components are very important. Specifications of components are very important. Then maintenance of components. Specifications as well as maintenance of components. It should not damage, and the frequency of failures should be less, right? Then only it will improve the reliability. So then control and minimize the effects of any failures that occur. Control and minimize the effect of any failure. Right. So this is basically the role of, there comes the role of relay, protective relay, which is the most important components, which is one of the most important components of the protection system, power system protection system. Its role is to control and minimize the effect of any failure. So basically the relay operates to disconnect a faulty part of the power system, thereby protecting that part and remainder of the system from the damage. So relay not only protects the part which has fault, it protects the remainder of the system from the damage, because if this fault is the effect of fault is there for a prolonged period, then it spreads, as we have seen in an example of transformer fault. It spreads and it may lead to a catastrophic failure. Now, coming to protective relays. Protective relays are placed on power systems to reduce the alternative links to a minimum. What is alternative link? Alternative link is alternate path for current to flow, for power to flow. So if there is a damage in a particular section, then if that section is isolated, or if that section is disconnected from the system, then if there is an alternate path for the current to flow, then it is good. But we need to minimize the number of alternative paths, then only the cost will be less. So the relays should be located or placed in such a location such that these alternative links are minimum. Okay, now relays locate faults. So the basic working of relay is like this. Relays locate faults and trips the circuit breakers. So basically the circuit breakers interrupt the flow of current to the defective component, thereby isolating it. So the relay is the one that senses the fault, then it gives a trip signal to the circuit breaker. Circuit breaker interrupts the flow of current. Circuit breaker interrupts the flow of current. Now, the relay is operated mostly at a low signal level. The signal level may be low for the relay compared to the actual system from which the fault is sensed. The actual power system is here. The amperes may be very high here. So this is sensed, and through some equipment it goes through and the signal level is reduced to a lower level, and at that signal level only relay is operated. Here comes the role of CTs and PTs, current transformers and potential transformers. Basically the step down of current and step down of voltage, so that the relay can be operated at a lower current level. So if there is a fault current or a current is sensed to be a fault current which is greater than the threshold value, then it senses that there is a fault, right? When I is greater than I threshold, some threshold. I'm using generic terms here. I'm not going to the specific terminologies now. From the next lecture onwards, we'll introduce one by one. So here the fault current is sensed, and the fault current is in maybe in range of kiloamperes maybe. So the current transformer senses this and steps down this current to a lower value at which the relay is operated. So for the relay, the threshold value is different at a scale down level, right? So if the operating current of the relay is at a smaller value, then at that value relay is operated and relay communicates with the circuit breaker. It gives the trip signal to the circuit breaker, and circuit breaker isolates the that section which is having fault. So two benefits are there because of the installation and operation of relay. First one is to minimize and prevent damage. Minimize or prevent, not minimize and, to minimize or to prevent damage to the faulted components. And the second one is quick response of the relay minimizes the seriousness and duration of the fault's interference in normal operation of the unfaulted components. Because if it happens for a prolonged period, as I already told you, this may lead to spreading of the fault, spreading of the damage. Okay, so to avoid that, quick response is required. Now, CTs and PTs. We have already introduced CTs and PTs. We have already discussed about CTs and PTs. So, PTs can be also known as VTs, voltage transformers. They acquire info. CTs and PTs acquire info or information about the power system in order to locate a fault. So what should be kept in mind while designing a protection system? Type and location of instrument transformers. Instrument transformers mean CTs and PTs. CTs and PTs. Okay, instrument transformers. Then the circuit breaker, selection of the circuit breaker, then signal level required to for relay. For relay, signal level required to operate the relay. So these are selected when the relay is applied to the power system for the first time, or when the relay is installed to the system for the first time. Type and location of the instrument transformers, then circuit breaker selection and location also. Mostly between each component, circuit breaker would be there so that each component could be isolated or disconnected from the system to save that particular component. Then signal level for the relay, how much the current level should be reduced to operate the relay with respect to the actual power system current, fault current. Now, another aspect is fusing reclosers. So I'm just broadly rushing through the topics which are to be discussed in this particular course: fusing reclosers and sectionalizers. These things can be used in place of relays sometimes to keep the cost down. Now, circuit breakers are located in between each power system component for disconnection. As I told you, there are 3 components here. So here one circuit breaker, here another circuit breaker, here another circuit breaker. So this can be isolated, this can be isolated. These components can be disconnected from the system and saved. Okay. Now, if there is 2 or more components can be simultaneously isolated also. 2 or more components, sometimes each component may not be isolated. Instead of that, we may have to disconnect both these components. So this circuit breaker will act and the whole section is isolated. So 2 components are isolated. That case can also be there. Now, another aspect is zones of protection. Zones of protection. What is the term zone? Zones of protection are very important. It's a very important decision to divide the zones for a protective, in a power system. This is basically the boundary of protective region. Boundary of protective region. We will see an example. It is required that the zones should overlap. Suppose this is zone A, this is zone B, this is zone B, this is the overlap region. Okay, zonal overlap region. Okay, so it is required that the zones should overlap. If fault is in the overlap area, if the fault is here in the overlap area, then 2 or more circuit breakers may trip, because a circuit breaker corresponding to this zone will be there and another circuit breaker with respect to this zone in this zone will be there. So both may trip at the same time. It may happen. We'll see the advantages and disadvantages of zonal divisions and zonal intersections. However, this area is relatively small, right? This zonal intersectional area is relatively small, and hence the probability of fault in this area is also less. Okay, now we will see the example for zonal protection and its disadvantage. Let this be a generator. Here we have a circuit breaker A, then here another circuit breaker B, then a transformer, and from here different lines are there. So we are dividing the zones like this. Suppose we are dividing the zones like this. This is zone A, this is zone B. Okay, so this is the zonal overlap region. Okay, now if you have a fault here to the immediate left side of circuit breaker B, in that case, which circuit breaker will trip? This is in the zone of circuit breaker B, right? So circuit breaker B will trip. Now, even though this circuit breaker trips, the problem here is the fault is on the left side, right? So the generator feeds the fault current, right? The generator feeds the fault current. So what should happen? Ideally, circuit breaker B will sense the fault, right? Or the relay, the relay corresponding to circuit breaker B will sense the fault, and circuit breaker B should communicate with circuit breaker A, right? Circuit breaker B should communicate with circuit breaker A, and A should also trip. A should also trip, right? A should also trip. Then only the generator will be disconnected from the system, and the generator will not feed the fault current. But what is the disadvantage here? If this is the generic approach, that means if at all B is going to trip, then it communicates with A, and if A also trips, then in that case, if a fault is there on the right side of B here, if a fault is there on the right side of B, this is F2, okay, this was F1. If a fault is there on the right side of B, then also if this is followed, if B communicates with A and A is also tripping, both the circuit breakers will trip. That is not required here. Tripping of B is sufficient, right? Tripping of B is sufficient. So although tripping of B serves the purpose, here both the circuit breakers trip. So zonal divisions are important. This is one, I mean, this is an example, disadvantage of zonal protection. Okay, so the division of zones and where to keep the circuit breakers, the operational signal level of the relays, then the location of CTs and PTs, all these are important. We will go through all these topics in this course.